So let's design Uber, or in general any such platform which provides cab booking services. Now, saying cab booking services is not more than enough, because we all know how actually Uber works. First we'll go through the screens step by step, and then we'll understand the requirements to understand exactly what at scale happens in a situation like Uber, Lyft, Ola, Rapido, in any such case. So obviously from a rider's perspective, we enter the from and to. Once we have done that, after some time we get a list of prices for different services. Now we select, let's say, one particular service, then we see our location, as well as the main thing is a loader that comes saying that waiting for driver to accept. And what happens parallelly in the driver's view, which many people do not know, but in case you might have observed, I will tell you. What they see is that they have kept their Uber driver app open, and there they keep getting requests. The request has a beeping sound, and in that notification alert they see the rider name, the price, the destination where they have to go, and they have a countdown like around 15 seconds. That is like a human reaction time that they decide, do they really want to go for it or not. If they slide up, it is equivalent to a reject, or if after the 15 seconds go off, it is equivalent to a reject. Otherwise they accept it. If they accept it, at a user end we see the driver name along with the OTP and the ETA, in how much time they will come, along with the routing in the map that they are coming to us. And parallelly, for the driver, they have the map opened for them. They get to see exactly which location they have to come to. And I have not drawn the next step, but the next step is also similar. We provide them the OTP, they enter it into their OTP, and they select start ride. When they start ride, again intent of Google Maps opens, and in the map they see from destination to destination, and once they end their destination, they go back to the app. There they have to do an end ride. That's it. Once they end the ride, they get to see the total fare details. So if let's say it was 50, here it will be 50 plus some delta. So that delta is because, let's say, they took a long route or there was a wait time in it. That kind of the rating meter or the way pricing is calculated, there is an increment to it. Now, having said that, let's try to understand the business requirements. Obviously, rider selects the ride. There is a price choice which has been calculated. Now we say it as a demand. We as in Uber or any other system, specifically Uber. I like that part. Driver is shown rider, and driver is actually the supply. Now that Uber states at a demand and supply curve, now that Uber states it as a demand and supply, it automatically becomes a demand supply matching problem, which they say as a dispatch problem. And this kind of similar design will be now used anywhere where there is a demand matching with a supply. For example, food ordering and all, which I will be discussing later in some future videos. But having stated demand and supply, there will be a supply demand created. There is a supply already present. There will be a matching happening at a rider to driver level. Once matched, then there will be a fare recalculation post the trip. Obviously, pre-trip calculation was present here. Now at the end of the day, a user is able to see the activity history view. Same goes for, like, even the driver can see the activity history. It's irrespective. Again, what is very important for Uber is the fare calculation. Why? Because there is obviously a base price, which is like a normal standard rate SR plus the distance into the normal base rate, whatever that is, plus the surge multiplier. This is very important. Why? Because it gives incentive to the driver that they, for example, this is a map, in this is a hotspot, means a lot of requests are coming. It pulls the attention of a lot of drivers to keep catering to this area. It's because of the surge multiplier. So Uber has a lot of other things, but these are the main features of a Uber or any ride hailing service that creates the match between a supply and demand and keeps the flow of supply catering to the demand via the entire process. So already I have said enough about what Uber at the base level is. So let's start thinking in terms of principle of software designs, that how it could happen. Now from our supply perspective, we will first consider who is our supplier, that is a driver. So let's say I have my driver over here. Now, how does Uber consider a driver, or how should these kind of platforms consider it? Driver is moving or in a state of rest wherever. Basically, there is a concept of lat long via the GPS, which we will have to track. Now a driver, if it is moving or if it is in rest also any place, and they keep their application open, they have to continuously communicate. That means they have to keep relaying this information to a server. Let's say this is my location service. Right now we are just thinking from first principles. Now because it's a location service, so it has to then update it into a location DB. This is my driver side. That is what Uber understands, that a driver is being in what particular location it is. Driver updates it and it is stored in my DB. From a rider perspective, again it will create a request, it will connect to via an API gateway. I mean, these are pretty standard. I will actually go into these things after some time. We are just trying to first understand on a very high level how it might look like. Rider via the gateway, it will connect to a ride request service. Simple thing, it will give its location via the API. I mean, I'm not going into the details of the API, but the post body would look something like it has given its from coordinate to coordinate. Now the ride request has to go to a price calculator, fare service. The fare service will consider all of this into picture. It has to calculate the distance. Now for that, Google provides its S2 service. It's a third party service. It will calculate the distance of from and to, and then it will apply multiplier of like the standard base multiplier, let's say 0.5 rupees per kilometer into the total distance that has been calculated, let's say 30 kilometers. But a surge multiplier should also be there. Right now let me black box it, saying that there is a surge multiplier, but because I have given a bit of it, so let's say there is a service surge multiplier, it will ask it will get the information and it will multiply this 30 into 0.5 plus the surge multiplier, say 20 in this case, and it is per service. It will create a list of services and it will give back a response. That's it. Now let me just separate this part out a bit. Now that it is a bit separate, I have some breathing space. The next part is rider accepts one of the fares. So rider, obviously via the gateway, it has to reach out. The moment it accepts, not accept, it's more like another post request or another API request is there, and it is like a trip, and a trip request is sent. Trip also will have the same details from to, but along with that the fare details. This is my trip service. Why? Because I will create a database. I'll create an entry to that trip DB. Now what that DB is, again we will come into it gradually, but let's understand how the design will scale up. My trip service reaches out to the trip DB, but now it has to do the matching, which is our most critical service. So the matcher, trip service reaches out to the matcher. Matching service now will query the, okay, this distance is very big, let me shorten it. Now that this is a bit closer, matching service will reach out to the geospatial index or location DB. I'll come to why I called it a geospatial index, but for now let's treat it as location DB. Once the matcher reaches out to location DB querying that, hey, for my given from location, which is my center, this is my ring, this is my map, in this radius give me all the drivers which are available. This response, when I get back, the matcher will use it to understand, okay, these all are my driver, let's say D1, D2, D3, and it has to then notify them back. So why not, for the sake of saying, create a notification service whose responsibility is to now reach out to the driver. So what driver does? Driver gets this kind of screen, and now the driver will have to accept or reject. Let's say it accepts. So it has to again relay that information back. Let's say for now there is a service for accepting, so say acceptance. It gave back the acceptance over here, which is relayed back to the trip because the trip has all the information. And obviously I'm not going to the schema details of it. And here we get back a response, not from the DB but from the trip service, that okay, this is our exact trip, basically this screen. And obviously then it can go via the state flow. There are a lot of things that I've abstracted out, and let's start thinking about it gradually. Now, at this point, the picture is also looking very dirty and messy. But let's use this as a reference, and I'll start drawing a cleaner diagram one by one. First, we told that driver is giving its latitude and longitude via the GPS continuously and getting indexed into the location DB. First thing to note it is happening continuously. That means the driver has to keep communicating over a WebSocket. Why WebSocket? Again, we have discussed this similar principle in a lot of other places. There are choices for us, either go via the REST API concept or go via the server-sided events SSE or WebSockets. In terms of when trying to get here, the driver is very chatty in terms of giving its information. If we go continuously via this concept that every time it has to give its update, it will do a put call or a post call, it's like a three-way handshake happening and unnecessarily leading to loss of bandwidth. And at the same time, there are also multiple notifications that have to come. So I have drawn a different service over here and drawn the line, but I will clean it up. Practically speaking, this all will happen over a WebSocket. Why? Because this is my client and this is my server. They have to keep communicating. Client keeps sending its location updates. Server keeps sending it dispatching requests, that is requests from the marketplace. So let me make a cleaner diagram at this point. Now there we go. As I said, this is our driver. There is a gateway. It reaches out to it. Obviously there will be upgrade of connection and then it will be converted into WebSocket. But assuming that it's a WebSocket at this point, it keeps sending its location. So there will be a location service and there will be the DB. Now, as it has a location service communication, obviously API gateway or this gateway cannot directly communicate with the DB. It has to go via the location service. Coming to the DB part, first we'll discuss about DB. It's an interesting topic, that what exactly should the DB of choice be and how Uber went with it. Let's assume we took SQL. If it were to be a SQL, then our table design would have been something like the driver ID, latitude, longitude, and some other meta information, but these three columns are the main important aspect right now. When any service here has to query it, there will be queries. For example, one query that I did, which actually Uber does most of the time, is that in a given radius, tell me which all drivers are there. Automatically count of it also will come out for search pricing. But the main thing is in a given radius. Now latitude and longitude, to convert it into a radius, we'll have to do what is called Haversian formula. Now this is not that important thing in this case. The point is the DB choice itself is problematic. In a ACID like, not like, but ACID DB, when we are doing writes, there will be locks and when we are doing a read, then there will be indexing into picture. The number of drivers that Uber handles is like 500 million drivers over the world. If we take a country like India also, if we go for a number like 5 million, these many drivers are updating into the table. That itself means the DB is continuously going through its life cycle of putting locks, and then there are updates happening. We generally don't do, even in structures like where we have to do add click or metrics collection. When the number of queries hitting, the right queries hitting is very high, we go for a NoSQL type database. Also, rather than directly me jumping into, because at this point we already know it's a NoSQL database, something of other interesting point is what kind of data is stored over here. Is it really latitude and longitude? No. Interestingly, let's say this is my map. In that, what Uber says is I will subdivide it into regions. Let's say, because I mean this is structurally how the decision making went. Later it will convert to something else, but bear with me. So it said that I will subdivide it into regions. I first divide it into 4 regions, then I take every region and subdivide into 4. So it's like a recursive step. Now two choices come from here. One, either I can represent it as a tree. That means first I represented the major nodes as these 4, then every other node as further 4. This is called quad tree. Now the caveat in this, or like something that I have skipped here, is there is something called K which decides further branching should happen or not. So let's say I make these kind of dots saying and I say assign K is equal to 3 over here. So that means any value greater than 3, if there are number of dots, and here dots represents drivers, intuitively that means Uber, why? Because Uber has to locate and pinpoint the drivers. This is the main supply point. Now if there is greater than 3, further subdivide. This box does not need subdivision, this does not need, this needs it. Again it will say okay, go recursively and subdivide. Now all of the boxes, they have 2 1 1 0. So the representation will become, and say I represented 0 1 2 3 in an anti-clock fashion. So this is my 0 1 2 3. This needs its own quad subchild. These all don't need. Now obviously in this all the nodes contain the driver location. For location, what Uber initially thought was it will convert and it will take a S2 index. Basically Google Maps provides that feature. That means here it will have a kind of a cell ID for it. The cell ID contains the exact driver metadata information, but that was being dependent on Google. The other way also it thought was, maybe instead of a quad tree, why not just go and keep doing in a granular level. There are differences between a quad tree and the second part that I'm talking about. Here I keep doing it recursively for all the individual cells, for this, and again I zoom into it. Here again I will subdivide. So if I named it 0 1 2 3, and here again I name it 0 1 2 3, so this particular cell will become actually 0 0. And if I take a 16 character long string, then that means I have subdivided my space into the 16th level possible sub level. That is a very fine tune. So Uber had the choice. So this is called actually geohashing. Instead of quad tree and geohashing, Uber completely opted a different path out of its research and development. It said that when I have to do a query over a flat map which is spherical in nature, and I do a ring query, my square kind of system does not work. There are a lot of offsets that are present. I need something which actually works in a square condition. it went with a concept of hexagon, which is in terms of Uber the H3 library that they built. The reason I'm drawing it out is to make you guys understand that what was the intuition behind it. It's the exact same intuition that powers. The more hexagons you build, the more you understand that a circle will not have that many offsets left. It can be completely covered by drawing hexagons altogether. That means if you have one hexagon location pinpointed, you can easily do a ring radius query. Obviously, I've drawn it in a wrong way, but I will give links to the H3 library, which they have open sourced, and they are able to do that query very efficiently. And it is actually a power up over geohashing. Let's say we would have gone with geohashing. Redis by default provides that geohashing, and many textbooks talk about it, saying that we just have to present the geohash into the Redis. It will understand it and it will keep storing it. Like, we don't even have to calculate the hash. Redis does it out of the box. But rather, Uber said that it will go via the H3. Now, so at this point, what happens is when the request comes here, the location service, first it will convert, and it will convert it into H3 of lat and long. It will send that information to the DB. Or now the DB, what should that DB be? Because we have understood that what Uber chooses as its main mapper function, but how does it get mapped into which DB? They could have gone with DynamoDB, Cassandra, but this is the time when the Uber was designing it. The DynamoDB paper was released, and that was a heavy inspiration for them. They designed something very similar in internal architecture to what today is the architecture of DynamoDB, that is the consistent hashing structure. And as per them, they tell it as ring pop. So I will put the resources links in the description for that. They designed it over Node.js. There is a reason at that time Node.js was very popular, and also it was giving its event loop. So they thought, in the DB is basically a cluster of lot of individual server nodes. Why not take a range of H3 indices and map it to one particular node? That means, let's say I take one city. So these are basically city clusters. I subdivide my city into different regions. So in this case, 5 regions are there. I map it in such a way the H3 indices range that come up over here. So this will fall into this node. Similarly, these all ranges will fall into this node. So as you can see, how and why this is highly available is because of 3 things that are coming into picture. 1, this structure uses consistent hashing. So that means the indices are pre-designed or pre-signed to one of the nodes. Second, there will be internal gossip protocol, which means this node at regular intervals of time, like let's say every 10 seconds or 20 seconds, will keep broadcasting to few set of members what are the list of driver ranges, or in this case not drivers, basically the list of H3 indices, the range of H3 indices it holds. So that way, if my request falls to any node, it can quickly identify, okay, if I am not serving this range, then who should I serve to? Because of gossip protocol, eventually all will have relevant set of information, and then it will forward it to that particular. So basically it follows similar structure to how the Cassandra or DynamoDB internally falls. There also it's similar. The ring is consistent hashing. There are nodes. There are range of data which after hashing has to be accommodated by the succeeding node. The main reason is, if let's say there is a failover of this node, only certain range of indices, or in this case H3 indices, have to be taken over and reassigned to another server, which in general case is a very hard thing. And also how it is highly available, it's because of I can quickly give, so basically there will be a load balancer over here sitting, like it's internal to this this DB, location DB. The only task is it will forward the request to whichever server has the least amount of requests. That's it. Now ultimately this will be forwarded to that server where this information is actually guaranteed, and the driver location is in memory stored over here. So in memory storage, the driver will have its own basically the driver information, like the driver ID, the current location that it is exactly in with its H3 index, and vehicle type and all. I mean, these are something I am adding, but driver ID and H3 index is more than enough right now. Let me now clear this space. This is what is we call geospatial index. I mean, it's just a new way of saying this particular DB. That's it. And now the next part is, we already said that this is a WebSocket. Say there was this matching service which I had told earlier. This will go and query the location DB. It will find out, basically the location DB internally has each driver, each node has, let's say, certain number of drivers. I get to know exactly which node, which query, and location DB responds back with list of drivers. It has to then obviously rank the drivers to whom to send. So the ranking happens in multi-stage. First, find out, obviously from here the filter itself gave it the active drivers. Then you have to do a ETA ranking, basically estimated time of arrival, because as per what Uber says, that matching the closest driver is not enough. So these are 2 points A and B, and here driver 1 is there, here driver 2 is there. It's not necessary that driver 1 should be matched with A. What if there is a heavy congestion over here and driver 2 can easily reach to A? So A should, Uber says that the wait time for the rider is crucial for Uber's app usage. So they match using ETA as one of the sorting factors. For that, there will be the ETA pipeline. Again, I am abstracting out ETA as of now, but say it sends out the same list of drivers to the ETA pipeline, ETA service, and ETA gives back the response. Now, it has to then notify back the drivers. Notify is not actual notification or push notification. It's more like when their application is open, they keep getting those pop-ups. Pop-ups as in they keep getting those cards. How to do it? That is when one thing that I had abstracted out is this API gateway itself, there will be multiple gateways. Why? Because the amount of driver that Uber handles, one gateway is not enough to handle that many WebSocket persistent connections. So this will be scaled. There will be multiple gateways, and each gateway will actually do a session registry. Let's say this is your Redis, in which it keeps the driver ID with a TTL. That's it. And the connection has driver ID to the WebSocket gateway ID. Now, once the matching service gets to know these, it will give the information to the dispatcher, because practically speaking, matching service is a very busy service. It's not responsibility to reach out to the drivers. It has calculated with the list of drivers, and the dispatcher will actually carry it in waves. So when we see our progress bar, basically spinner, what happens is in wave 1 it will reach out to the first 3 drivers, then in wave 2 it will reach the next 4. Similarly, it will keep exhausting the driver list. This will query the session store. Let me clear it a bit. So the path will look something like, after the matching service, it delegates it to dispatcher. Dispatcher now has to keep sending it, basically communicate with the session store to identify exactly which gateway to use to send this information back to the driver over the WebSocket. So once it does, the driver gets to see it and they have a choice, accept or reject. Now, because the entire thing is scaled up, that means matching service itself is not one matching service. Even the dispatcher is not one, there are multiple. But think about it. Let's say multiple requests are coming, A, B, C. These are the riders and these are the drivers, D1, D2, D3. Say all of them are from the same region for the sake of simplicity. And what happens is rider A's request can be matched to D2 and D3. Similarly, B's can be matched to D2 and D3. C1 can be matched to D2 and D3. So from this, I'm trying to say a driver can get multiple requests at the same time, and one rider's request can go to multiple drivers. We don't want both of the things. One, a driver should at a time only see one request. That means in his application here in the card, only one request should come. Only after he rejects, another request should come. How can that happen? Because here the matching service is scaled up and its main point is only to query the location DB, do the proper, basically accumulate. It will reach out to the ETA using the list of drivers it has got from the geospatial index, and it will then do a logical filtering and ordering, and it will then delegate the response to the dispatcher. Dispatcher is then going and dispatching it via communicating. I will not repeat the same flow. Because of stateless nature of the services, the chances A can like start, multiple requests can start going to driver. That means we need something in place. So before the dispatcher can send a request, or when the dispatcher sends a request, actually in this case, we keep a Redis cache. Why? Because we are following a concept of a temporary ephemeral lock. What we do is, I'm putting it over here, set driver ID, by default it is true, with a TTL of 15 seconds. This is my TTL. So that means when the dispatcher has to actually dispatch, it will do a query to the Redis to see that if driver ID is present or not. If the driver ID is present, that means already some other dispatcher or some other thread has done a dispatch to this driver ID. That is, it is in this state where it has got the request, and I am not sending it another. Let that exhaust naturally, or let it cancel. If they cancel it, then again via the WebSocket I get the communication back, and it will be relayed to my dispatcher actually over here. This part I'm not drawing because it is intuitive over here. It will reach out to the dispatcher and then it will cancel it out. But in case generally drivers don't, which is a case, they just let it happen. 15 seconds is a very normal time. It will anyways expire on itself and they will get the next request, because there are other dispatcher is continuously loaded with a lot of matching tasks. Now we have solved one case, so I will be decluttering these arrows as well. At a given time, A's request can be broadcasted to D1, D2, D3, but there is no way that I am ensuring that if let's say D2 accepts it first, D1 and D3 cannot. What do I do now? There are actually two ways to go ahead, and we will be actually applying both the ways. One is using Redis only as a distributed lock, which means say my dispatcher, it has broadcasted to a D1, D2, acquire lock and create the transaction D1 to A mapping, and that's it. When this will try to acquire lock, it will get cancelled because this acquired the lock. So basically it will also have an equal chance D2 to A, but because this entered to acquire the lock first, this will not be able to acquire the lock. For this we can create another Redis entry. Basically we can direct both to the Redis entry, but it will look something like this. We'll be doing a set, then lock. Key name can vary, but let's say ride, the ride ID, let's say R1, then drive A, ID again, that is ID, NX, That means create lock if does not already exist, and then an EX. Again, EX is so that deadlock does not happen. Let's say EX of 5 or 10, because transaction will take that much time so that the lock gets expired. So this is the requester. So this is the request ID. This is the entire lock key for that particular ride. And this is the exact thing that Redis will have. But we are not completely relying on it. That means there will be an assignment service. So from the same WebSocket, the driver, when accepts a request, will come over here to the assignment service. Now, a few things that I had not discussed, but there will be a DB where we are keeping store of driver state and the ride, these things. Like I will fill up the columns in some time, but there will be ride detail, driver detail, and the ride assignment. The moment we get this information at a database level, the main reason for talking about these tables right now here is there will be a transaction happening at this point. These tables will be the participants here, and the lock will actually, so the main purpose for this entire discussion is we don't want two competing drivers. They have already acquired a lock from the Redis level, but we also want to make it sure that the single transaction happens and only one participant or one candidate wins. So let me just paste the SQL over here. We will discuss briefly a bit, but we will also talk that how it makes sure that we are able to get our consistency here. So this begin and commit, they are the part. So this says that it's part of one transaction. Now this is the trips, and this is the ride assignment, and this is the driver, which I had kind of said. In trip, the main thing is we are setting its assigned, and here this is the main thing, the where clause. So let's say driver 1 and driver 2, they both are trying to accept it. One of them enters first, and we are setting assigned for that driver where it is either in the searching state or offering state. In the where clause, when the ride ID is coming into picture and the status clause is there, because it has already been assigned, this won't work. So automatically for driver 2, the moment it has done its assignment, it will not be able to assign anymore. It will get a null back from here. And in the UI, driver will say, sorry, this ride is no more like existing. Now, as we have started our journey in the trips part, we can go into the ride assignment as part of the entire single transaction. We will get our, basically we have to enter this into a ride, that for that particular ride, who is the ride driver. And this is basically acting as a, like a in between table between the trip and between the driver. So we are taking the ride over here and the driver over here and assigning it in between the ride ID, the driver ID, the status, and when it is created. And finally, in the drivers table also, what we will do, we'll put the driver. They must be either in the available state or soft held state, and from there we are changing it in the assigned state. All of this part of one transaction. Why did we get deep into this? So when I said here we have put already a Redis, basically the assigned service. Let me draw the Redis over here and put this arrow here. Yeah, so when we are already putting a lock with the requester driver A, and if it not exists, then only put a lock, and if it exists, then automatically we'll get a null here. We'll get a 0 or whatever is the return ID over here, and this will be for TTL of, let's say, 5, because we are assuming that the assigned service is able to make a transaction into DB within that 5-second time. Let's say there is lot of load on the assignment service even after scaling, and it takes more than 5 seconds. It takes 10 seconds. Then this lock will get over. Now driver A and driver B both are able to enter into this. If we had not put this kind of a guard itself, then both would have thought that they have won the race, which is not the case. The other thing is, let's say assignment service fails due to any reason, then also the same situation. And what about Redis? Redis is also not a very it's not that it is always active and alive. Maybe due to heavy load, even the Redis is an ephemeral state and it has gone down, then there is no point of truth at all. This guard at a database level will help us out. So this is a very common recurring pattern. It will happen in the later system design videos also, that when a entity, there is a race condition happening, when both of them try to win over that, we have to put a distributed lock, and it is done in two steps. One, using Redis as the source initial entry barrier, and then also in the DB doing a state management. The entire work is happening because of this state. If we are able to manage a state of a trip, which is between a searching state and offering state, then only they go to assigned. Now what this state are, I have not discussed about it because we were going from a driver's perspective. Let's for some time change the track and try to see the states. I have already drawn the state over here. So this is the trip state. First, it is quoted. Rider confirms the quote, then it goes into the searching state. From searching state, if a candidate driver is found, it goes into the offering state and gets assigned. Otherwise, there is a loop. First, like what we see, we are in the searching state for a trip. Then no candidate driver is found for it. It again goes to searching state. But if there is an offering happening, like I directly did a short circuit and told that it's in the assigned state. Now from assigned state again, driver could be arriving, or it can go to cancel state, or from assigned state again automatically it can go to cancel state, or I as a user, which I generally do, I go from searching state to cancel state. Or otherwise from a driver arriving state, it can go to arrive state. Even when the driver has come to the location, then also it can go to cancel state. Driver due to some reason interacted with me and thought of cancelling it, or I told the driver to cancel, whatever it is. Then we come to the in progress state. This is the entire, now the trip, when the OTP is given, then this part happens. Like after this, from after the arrive, this entire thing happens. This cannot go in between that. From in progress, it has to go via the completed and to paid. I won't be focusing over here because this is a very normal easy flow. So now that I have introduced my assignment service, let me clean this up a bit more. Now, since the board is clean, we are actually in a very clean and happy state. This entire part will be by the rider side. I will come and draw this part out. But say there was a trip and it has gone into a matching state, like via the matching service. We went to the geospatial index, we queried the certain set of drivers. And again, one arrow that I had missed is from the same DB, it has to query the drivers which are assigned. So basically, continuing the narrative over here, matching service reaches out to the geospatial index. We find out the particular query index. Basically, this location is a black box and it will return it the list of drivers. Now dispatcher, using the Redis, it will put a expiry time here that okay, this particular driver, I'm sending out request to this, others please don't send. Using this as a set statement over here, it sends to the session, like it communicates with the session store to find out exactly which driver is connected to which gateway via the WebSocket, and it sends that information. Dispatcher service will send that information back. Okay, I have not drawn that arrow. It will give out to the gateway and the information will be relayed back. Now, one happy driver accepts that, say, let's say multiple drivers, in this case, try to accept it. One of the drivers, both the requests reach from the gateway to the assignment service again. We already put a Redis lock over here to make sure that this resource is basically a resource lock, and driver A, the one who is doing the first request, is able to acquire the lock and able to complete the transaction. They reach out to the DB and they make these entries over here, which I had showed. We update the trips DB, we make the entry into the ride assignment, and we also update the driver DB. Now the only part remaining is the rider part. Due to the entire story started because the rider had created the ride. So now we introduce our rider. Again, the rider, there is a API gateway, load balancer come API gateway. It made a request to the riding service, or say trip service. I mean, I'll name it out accordingly. From the riding service, there was a fare service calculation. It reached out to the fare service. It used both the information. The main thing is it reached out to a third party. Okay, I have the space over here. It will reach out to the third party to calculate the distance and then apply the normal mathematical function, as well as it will reach out to the ETA service as well. This ETA service can also directly communicate with the location service. Actually, it has to communicate with the location service. I am abstracting it out, but obvious reason is ETA needs to understand that how is the location mapping happening, but I don't think it needs to. Sorry if I am saying so. It does not actually need to reach out to the location service. My bad. ETA service can act independently here. Actually, in the map, again, if I have to reach from A to B, we apply Dijkstra. But in a case of map which is converted into a road graph, to make it much faster, we do bidirectional Dijkstra. From here also we start shortest path from here, and somewhere in between they will converge, and that the time it takes basically on that route with a given constant speed, that becomes our ETA. So it is a dedicated different service. Fare service will reach out. Now, once the rider accepts it, there will be a trip service, because this is a trip. The trip is in place, so it will create an entry into the DB, that same trip that we were talking about in this, sorry. So in this trip, we already have the ride ID in picture. It's the driver ID only which needs to be assigned, and the trip will be by default in the searching state. So this trip service, let me just make the diagram a bit better. So the trip service will be, so from the ride service, it will delegate to the trip service, and from trip service, we will create an entry into the DB, as I have already discussed what we are talking about over here. This is the trip service, and here we will be taking, this is in the searching state, and this will be delegated from the trip service to the matching service. Now this does not, when I draw direct arrow between services, that means it will wait over here. It doesn't need to actually wait. Here we can put it into a message queue. Trip is just responsible for making an entry into the DB, because this service is not responsible for making an entry into the DB. Trip DB directly makes an entry into the DB, delegates it into the queue, and then it will be picked up by the matching service. And from here onwards, the entire journey that we had spoken about from the driver fulfillment scenario, that has happened. And now finally, when the assignment happened, it can directly now go and say the riding service. Basically, just to say, there are a few requests which are happening on this path using the REST API. But from the time the trip has been started, and which we also see in our thing, that waiting for driver, this will happen over WebSocket, because the server has to push that information over here. We cannot even do a long polling, because we generally see that it happens over a window of 3, 5. It can keep expanding. So this is not somewhere we can block the call over a REST API, and it should not even be an SSE at this point. We also keep changing our location when we walk, if you have noticed. So it will be again in a WebSocket connection. So obviously I'm abstracting out a few things over here, but a new WebSocket service will be opened over here, via which the trip actually happens, and then the trip will reach out. So let me just draw it out. There will be a WebSocket dedicated gateway, because obviously upgrade happens of the connection. So via this, the trip will actually start working, and the moment the assignment happens, it will reach out to the WebSocket gateway. How? Again, there will be a session store which says that okay, this particular gateway and rider are connected over here. It will reach out using this, and it will pass this information over, and in the WebSocket we see exactly which rider is assigned to us. Now we can also delegate it to the notification service, but then this is not the main thing in the design. Obviously, if we have closed the app for some time, then we can pass it into the notification service. From notification service, using a Android push notification or Firebase FCM, we can delegate it to the rider as well. Then we have to enter it into the queue, but these are not exactly part of the design of Uber that we are focusing on. The major part was actually to deal with how the entire supply to demand matching is happening. During that discussion, I also spoke about the how Uber is actually mapping all the drivers into its location DB. This I could have drawn as a simple diagram as location DB, but I wanted to highlight the ring pop structure also. That is why I drew it a bit bigger, eating away a lot of piece. So now we can see from again the happy path, the rider puts a request, it's accepted, delegated to the fare service, and then using the ETA service, final fare calculation with the surcharges in picture is then giving back to the rider. Also, now once the rider accepts it, a trip is going to be created, so it is passed to the trip via open WebSocket connection. From the trip, we reach out and create a table into the DB, and we also pass it into the message queue because trip can no more be blocked over it. Matching service will take some time. It's a long process because the matching happens in waves. We have passed it information to matching service. Matching service will now reach out to the location DB, find out the list of drivers. You know the story over here, but to repeat, via the list of location drivers, we also have to find out the drivers who are available at this point, filter out, and then we will be passing this information back to dispatcher because we have to sort it actually based on ETA, which we have done over here, and the list of drivers who are available. Then the dispatcher will understand, okay, I have to do it in waves. It will now reach out again to the session store to understand which driver is connected to which WebSocket gateway, and it will pass that information over here, which is gone to the driver from the WebSocket. Say a driver is accepting it, then it goes to the assignment service. Assignment service in the Redis will put a lock over that request, and it will also make an entry transactional commit into the DB, and it will pass this information back to the WebSocket to the rider as well. Also, when I was talking about here in the dispatcher, when it has to send back this information to multiple drivers in a broadcasting way, then it will again make an entry into the Redis stating that I am sending this dispatch event to one particular driver. Other dispatching requests, please don't send to this driver until it expires. Now let's go and see what and all we covered up in our functional requirements. Rider is able to select the ride. Driver is shown the rider. We are able to match rider and driver matching. Fare calculation. I mean, obviously, how the fare is calculated, that algorithm Uber has not disclosed yet. So even I am not able to. I can take a guess at it, but that is not the current scope of this design at least. Maybe I can go into a future video to actually calculate the surge pricing. That is pretty interesting. How surge pricing is calculated. Here I just said this is fare, but if you think about it, the fare needs to know that how much demand has happened. So here some other the moment location lookup is being done, this event can also be passed into a Kafka queue, and then some recalculation can be done. A global map can be stored where we keep exactly for one location ID how much count is there, like how much demand has been done so far. Using that, the fare can estimate that okay, this much demand has happened, so surge, put a global multiplier of that surge, or maybe directly here we can put. So I mean, this design itself is a broad place. Then there are other things. Do we every time have to do an ETA, or we can apply a machine learning model to just see between two distances? These are things which Uber does in its own research and development lab. But overall point is we have done all of this. The only part remaining is the activity history view. Now just to give a brief summary over it, because this design does not take care of the entire thing. It only has dealt with the above 4 business requirements. For activity history view, when the trip started, from then onwards, whatever location, let's say this is my city map, the driver is going, these all GPS, because this driver is in a engaged state in the trip. By that I mean the driver is already assigned to that particular trip. He was either available or softly held. Soft held is an intermediary step, but that is when the driver is supposed to like acquire. Then for some time it was soft held, and then it went to then it goes to assigned. But for the time being, from available when it went to assigned, from then onwards we are no more interested. Like any other matching service will not go and check this driver, but its location is still being tracked. So as per what I read in Uber's paper, what they were doing, same, they have a DB which continuously ingests a lot of location updates. In this case, now they are using Cassandra DB. Now this is strange. I mean, to be honest, I will give a bonus statement after this entire discussion ends. All the GPS locations that they have tracked, they kind of overlay here in the Cassandra DB, and then they say that GPS locations are not at all accurate to make a entire reconstruct the entire journey. Why? Because GPS is a rough estimate, and they say they have to do a map superposition, and for that they run another set of machine learning model and another set of algorithm. But think of it as they get these kind of coordinates. I'll draw with a red line, this, maybe somewhere here in straight places this is correct, but these places. So now when they have to do a trip calculation, they will do a superposition, and for this they are saying that Cassandra is meant to be write heavy, this is not read heavy. They create a cache and then they take the entire value over it and put it into the cache. Then there is this map superposition. It will read from the cache rather than from the Cassandra DB, because read and writes are happening at the same time. They don't want to overload the DB at this point. The map imposer service will read from this cache and it will do the superposition, and this is what is actually stored as a continuous graphical structure which forms as the activity history view. The main reason why I kept it at the end is because this is not exactly the business requirement of Uber per se. It has done it to keep its own account keeping and also a final calculation of the fare. This will need its own ingestion pathway, which is basically, if we go to this clean diagram, it has to do with here the driver when it's emitting it now from the location service. Another we have to open up a DB channel over here, keep updating into the right. The moment the trip will end, when the driver will emit that trip has ended via this DB, which entry happened in the Kafka queue or in any messaging queue, because it's a heavy calculation again, like this happens very fast though. It will pass it on into the queue, and then from the queue the map imposer will take place and it will again do a calculation using the fare service, and this will now get stored again into the DB. I mean, I'm pointing out to one common DB, and then again both the rider as well as the driver will be notified. So that is what is happening. Obviously this topic has become very big. I think I might create another topic to discuss about this requirement, then the activity history view. But overall, the other requirements are the major important requirements for any riding service. Maybe in the future video, in a recent future, I might be discussing about it separately, but all the resources via which I was able to come down to this discussion, I will list down them in the description below. See you folks till next time. Obviously in these videos there are a lot of discussions happening, not in a clean way but in a more jittery way, because the main goal was here to understand how we have to think from ground level rather than me presenting the entire idea in one shot. We have built it thinking and asking of different questions, like why we could not go with a SQL DB over here, where we needed acidic basically acid confirmation. Like this is a SQL DB, but this is a NoSQL DB. Like the structure is actually a NoSQL structure. Similarly, where we are applying Redis and for what reason we are applying, what different services will be present in this place, why a queue is kept. Because of these discussion reasons, this kind of become a bit of unpolished. My future goal will be, when I'm putting future videos, that I'll try to make it more polished, but the intention will be very different. I will be assuming that people who are watching those kind of videos are already aware of these informations. So these videos will also exist, but there will be some polished video coming in the future which will also exist. Overall, if you like the video and you have learned a few things in this entire discussion, do like the channel, do like the video, do share this video with your friends or people who you think would learn a lot from here, all the engineers who are out there thinking how these all things are happening. Please do share the video, and at the end, if you subscribe to the video, that gives me more motivation, and I will be digging deeper where there are a lot of things to be dive depth into, and those videos will be coming soon. I will make those videos faster if there are more shares and subscriptions.